All right, let's get started. We're talking this week about matrix population models. And this lab 4, is your chance to get some hands-on experience with matrix population models. This isn't always everyone's favorite topic in population ecology, but it is a fundamental concept of population ecology. It's tremendously useful for modeling populations, and it's definitely worth wrapping our heads around and taking some time with. So what I'm asking you to do is to step out of your comfort zone a little bit and don't be afraid of matrix population models. That is a barrier to learning. Let's just get right into it, and hopefully it won't be as difficult as you might think. It's relatively straightforward. We're talking today about matrix multiplication, which is obviously a topic that most of you have not encountered yet. Some of you may, if you're mathematically inclined and you're taking something like a linear algebra class as part of your undergraduate program, but most of you, I know, are not doing that. It's not a required part of the wildlife curriculum, and it may be a little scary. So the first thing I'm going to ask you to do is just don't be afraid of this. This is not that difficult. Let's walk through it together. You have 2 weeks to do this lab. Hopefully by the end of those 2 weeks, you will feel comfortable working with matrix population models, knowing what they do, how to harness the power of matrix population models using tools like R and Insight Maker. And that's what this lab is all about. So the first thing I wanted to do before we get into the R and introduce you to the questions in this lab, what I'd like you to do is to go to the whiteboard and to build a matrix population model from scratch. And we'll walk through the mechanics here of matrix population models. And what we're going to end up doing is basically running through a matrix multiplication operation. And hopefully it will even make sense. So where I like to start in talking about matrix population models is just to acknowledge that matrix population models are a type of discrete population model. So if you want to compute the population at time t plus 1, you multiply it by lambda. So you multiply the population at time t by lambda. That should be a multiplication. You multiply the abundance at time t by lambda in order to estimate what the population size will be next year. That is the basic discrete exponential growth equation, right? We all know that. That was part of lab 1. So that's discrete exponential growth. Now, what we're talking about here is actually very similar to this discrete population growth equation. So this is, there we go. So what we're going to do here is we're just going to be replacing lambda with what's called the projection or transition matrix, right? So this is called the projection matrix. This is the projection matrix or the transition matrix. And we're going to multiply, and we'll get into that in just a second. We're going to multiply this. This is where the matrix multiplication comes in. So this multiplication symbol represents matrix multiplication. Multiply that by the abundance at time t, which is going to be, let's say it's the abundance of hatchlings, the abundance of juveniles, and the abundance of adults. All right. So when we say, when we're talking about abundance in an age-structured population, we're talking not just about one number, we're talking about as many numbers as we have stages. So in this case, we have 3 stages: hatchlings, juveniles, and adults. So we're keeping track of the total number of individuals in each of those classes: the hatchling class, the juvenile class, and the adult class. All right. And if we multiply that by this transition matrix, then sorry, this should be time t. If we do that matrix multiplication operation, what we're going to get is the abundance of hatchlings, the abundance of juveniles, and the abundance of adults at time t plus 1. All right, so that is how closely analogous this procedure is, this matrix population modeling, is to the simple multiplicative exponential growth equation for discrete population growth. Lambda times n at time t is equal to n at time t plus 1. The projection matrix times the abundance vector at time t is equal to the abundance vector at time t plus 1. All right, so that's where I'd like to start. And let's just flesh out this projection matrix. What is that projection matrix actually look like? Remember, the top row of a projection matrix, first of all, it's going to be, let's see, hatchling, juvenile, and adult. So remember, a projection matrix has the same number of rows and columns. Each row and each column represents one of the stages. So hatchling, juvenile, and adult. This top row represents fecundities, and all the other elements in the matrix represent some type of survival. All right, so that's what we learned in class this week. And you also learned that to interpret every one of these elements in the matrix, you basically say it's the transition from what you are in the column name class this year. It's the transition into whatever the row name is next year. So to make that clearer, let's say this top row is fecundities, right? So this is the fecundity of hatchlings. This is the fecundity of juveniles, the fecundity of adults. And this is, let's say, we'll call G for growth. This is the probability of a hatchling this year surviving and transitioning into the juvenile stage next year. So I'll call that G sub H for the probability that a hatchling this year will survive and grow into the juvenile stage next year. All right. We have this element here in the middle of the matrix is going to represent the probability of juveniles this year surviving and staying in the juvenile class next year. I'm going to use the R term for retention. Some people use survival to represent this process of staying in the same class, but I don't like that because that's confusing, because survival, you can survive and you can transition onto another stage. That's still surviving. So I'll use the term retention. So this is the probability of surviving and remaining in the juvenile class. This is 0 because adults can't go backwards and become juveniles. The hatchlings cannot grow into adults, so I'm going to put a 0 there. Juveniles may be able to transition to adults, and that is a growth. It's the growth of juveniles. Juveniles this year transitioning into the adult class next year, right? And this is the retention of adults. So the probability of an adult this year surviving and remaining in the adult age class next year. All right. So this is our transition matrix. Every element representing the transition from whatever the column name is to whatever the row name is next year. All right. And so these fecundities, you can see the adults this year, if they survive, they can produce offspring in the next year. So this fecundity is the chance that adults this year will survive and produce offspring next year. That's what that fecundity means. Fecundity is a compound parameter. It basically has a survival associated with it and a birth rate or reproductive rate associated with it. So why did I put a J there? That should be the fecundity of adults. That's the sub A. So fecundity of adults is the number of hatchlings that an adult this year is expected to produce into the population next year. All right, so it has to survive in order to do that. This F sub j is the number of hatchlings expected to be produced by juveniles this year in the following year. So you take the number of juveniles this year. How many hatchlings are they expected to produce into the population next year? All right. And this fecundity of hatchlings means it's the number of new hatchlings that is expected to be produced into the population next year by all the hatchlings this year. All right. So that is what fecundity is. We talked about how that's a compound parameter. So the fecundity of adults, for instance, is equal to the survival of adults, right? In this case, we'll call it R sub A. That is the chance of surviving and remaining in the adult class times the birth rate of adults. All right. So that is how you compute fecundities. This is a common error that people who are putting matrices together fail to account for the survival term. The juvenile is even a little bit more complicated. So the fecundity of juveniles is equal to, you have the retention of juveniles. So if you survive and stay juvenile, then you might produce offspring as a juvenile at a rate that might be lower than the adult rate. And then you add the probability of growth into the adult class, right? And then you multiply that by the birth rate of adults. So you can add both of those terms in order to compute what the overall expected fecundity of any juvenile is this year. That is how many offspring next year are going to be produced next year by those that are juveniles this year. All right. And then the fecundity of hatchlings is also a compound term. It involves the basically the growth of hatchlings into the juvenile class, and then you multiply that by the birth rate of juveniles. So that is just a quick review of how we think about fecundities in these matrices, because I just want to point out again that that is a common error. We really have to think through what we mean by fecundity in order to really make sure we parameterize it right. We have to remember that we're talking about the number of hatchlings produced next year by individuals in the juvenile class this year. So those juveniles could stay juvenile, or they could potentially transition and become adults, in which case they might have different birth rates. And so we just have to, as long as we have a firm grasp on what these transition rates mean, then we should be able to put the proper numbers in there. But it is not, that's one of the hardest parts of putting a matrix together. All right, so let's move on to talk about matrix multiplication. I'm going to just erase this so I have more space down here. And what I'd like to do is, let's see, we'll start here. Okay. So let's try to compute let's just think through how we would compute the number of individuals in each age class next year based on the individuals in each age class this year. All right. So we will start by thinking about the number of hatchlings at time t plus 1, the number of juveniles at time t plus 1, and the number of adults at time t plus 1. All right, and let's start off with the adults, but we're going to go through the equations for all of these, but let's start with adults because it's a little easier. To get the number of adults at the next time frame, we're going to have to, or the next time step, we're going to have to take the number of juveniles this year, right, the juveniles at time t, and we multiply that by the growth rate of juveniles. That is the probability that juveniles survive and transition into adults. And then we just have to add the total number of adults at time t and multiply that by the survival and retention rate of adults. That is the probability of surviving and remaining in the adult class, right? Pretty straightforward. in order to become an adult next year, you either were a juvenile before and you survived and became an adult, or you were an adult last year and you survived and remained in the adult class. So that should be relatively straightforward. Similarly, the total number of juveniles in the population at time t plus 1, you can compute by first taking the number of hatchlings that were in the population at time t, multiplying it by the growth rate of hatchlings. That is the probability of surviving and transitioning into the juvenile class from the hatchling class. All right. And then you may want to add the total number of juveniles in the population at time t and multiply that by the retention rate of juveniles. That is the probability that each juvenile will survive and stay in the juvenile class in the following year. So in order to compute the number of juveniles next year, you take the number of hatchlings in the previous year, multiply it by the chance of surviving and growing into the juvenile class, and then you add the total number of juveniles that are expected to remain in the juvenile class from the previous year, right? So it's, again, very analogous to this computation of the total adults in the population next year. We're just considering you either survive and grow to the next class, or you survive and stay in the existing class, the class you were in the previous year. Now, this is slightly different, but again, not super complicated. In order to compute the number of hatchlings, new hatchlings born into the population next year, you have to take the total number of hatchlings in the population this year, multiply it by the fecundity of hatchlings. That is, how many offspring are expected to be produced next year by every individual that's a hatchling this year, right? Same thing, you take the total number of juveniles in the population at time t and multiply it by the juvenile fecundity. And that's the total, this is the total contribution of hatchlings into the population next year by hatchlings this year. This is the total contribution of hatchlings into the reproductive flow. That is the total number of hatchlings produced next year by those that are juveniles this year. And this, of course, take the number of adults this year and multiply that by the fecundity of adults. And that is the total number of hatchlings expected to be produced next year by all the adults in the population this year. All right, and now it should make even more sense why these fecundity terms have both a survival and a birth rate associated with them, because we're not talking about the total number of births this year by hatchlings this year, or the total number of births this year by juveniles next year. We're talking about the total number of births expected to occur 1 year from now if you are a juvenile right now. And this is the total number of births you're expected to produce next year, 1 year from now, if you're an adult in the population now. So in order to account for that time difference, some of those adults might die, and they won't have a chance to give birth next year. Some of these juveniles might die, and they won't have a chance to give birth next year. So that's why we really have to incorporate survival, these survival terms, R and G, the retention and growth, into our fecundity estimates. That is critical. All right, so let's think about what we just did. We have taken the total number of hatchlings, juveniles, and adults in the population at time t, right? And we've used those to compute the total number of hatchlings, juveniles, and adults at time t plus 1. Now, what we've just done is matrix multiplication. And let me just show you why. So this process here is matrix multiplication. Multiplication. We have just done it. Hopefully it made sense. Let's explain exactly how this works. In matrix multiplication, in order to compute the number of hatchlings in the population next year, what you do is you take this term times this term plus this term times this term plus this term times this term. What is that? That's the fecundity of hatchlings times the number of hatchlings in the population this year. That is this. That's the number of hatchlings expected to be produced by the hatchlings this year into the population next year, right? And then you add this term, F sub j times nj. That is the number of juveniles at time t. So this is the contribution into the pool of juveniles that are entering the population next year that are produced by those that are juveniles this year. And then you add this term here, the fecundity of adults times the number of adults. That gives you the expected contribution of hatchlings into the population next year by all those individuals that are adults this year. If you add those all together, you get the total pool of hatchlings that are expected to be entering the population next year, regardless of whether they were born to those that were hatchlings, juveniles, or adults the previous year. It just gives you this number here. That is the total number of hatchlings in the population next year. All right, so to matrix multiply something, you just take this top element, multiply by the top element of this vector, and then you add this second element, multiply it by the second element of this vector here, and then you take the third element in this cross row, this fecundity row, and you multiply it by the total number in the final element of the abundance vector here, and that gives you the total number of hatchlings in the population next year. Just the same way to compute the next elements, that is the total number of juveniles in the population next year. You move to this juvenile row, you multiply this first element by the total number of hatchlings. That gives you the total number of hatchlings this year that are expected to transition and survive into the juvenile class, which is what we're focusing on here. This next, then you add the total number of juveniles that are expected to remain juvenile. Of course, they're expected to remain juvenile, so they're going to also be entering this juvenile class. And then you take the total number of adults that are expected to revert into juvenile, which is 0. So you just add 0. And so you have these two entries into the juvenile class. And to get the total number of adults, you take the total number of hatchlings that survive and become adults in the next year, that's 0. And then you add the total number of juveniles that are expected to transition and survive into the adult class, that's 1 input. And then you add the total number of adults that are expected to survive and remain adults, right? So you can think about this as, for the hatchlings, you have FH times N. That's 1 input. So that's FH times NH. That's the number of hatchlings this year, the number of offspring that are expected to be produced into the population next year by hatchlings this year. Then you have this term, FJ times NJ. So that's FJ, NJ. That's the total number of offspring that are expected to be produced into the population next year by juveniles this year. That's the other input. And then there's a third input, that is FA, NA. That's the total number of offspring that are expected to be produced into the population by all the adults in the population this year. And you just add those inputs together, and that gives you the total number of hatchlings. You have 2 inputs for the number of juveniles into the population. That is GH times NH, hatchlings growing into juveniles, and then you have juveniles staying juveniles. That's the retention of juveniles. So you have 2 inputs, you add them together, and that is the total number of juveniles. And the same with adults. You add up the number of juveniles that transition and survive into adults, and you add in the total number of adults that stay adult. And that is how matrix population or matrix multiplication works. And that's what you do in R when you are doing a projection exercise with a matrix population. So when you're trying to project into the next year and the year after and the year after, using a matrix population modeling approach. Just a quick review of matrix multiplication here. This isn't like standard multiplication. This is a little different. And what we're doing is multiplying a matrix, this transition matrix, by the vector of abundances this year. And in doing so, we're basically computing the total number of individuals expected in each of our age classes next year at time t plus 1. So in order to compute the number of hatchlings at time t plus 1, we're going to take all the information in the top row and all the information within this abundance vector, and basically it's just the FH times NH, FH times N juvenile times F juvenile plus N adult times F adult. Right, so we're taking all the information in the top row and all the information in the previous year's abundance vector in order to compute the total number of hatchlings next year. And the same thing for the number of juveniles. We're taking all the information in the second row and all the information in the abundance vector in order to compute the number of juveniles next year. First, you take the number of hatchlings in the previous year, multiply it by the transition of hatchlings to juveniles, and then you add the total number of juveniles and their retention and probability of staying juvenile. And you can add this zero, number of adults times 0, because 0 adults are going to go backwards and become juveniles. So that's how we compute the number of juveniles next year. And the total number of adults next year, you take 0, so the number of hatchlings last year, multiply it by 0, because no hatchlings transition directly to adults next year. And then you take the number of juveniles, multiply it by their chance of surviving and growing into adults. And then you take the number of adults previously times the probability of surviving and staying adult, right? And so that is using all the information in this third row and all the information in this vector. And so that's what matrix multiplication is all about. And that's hopefully an intuitive explanation for why we can use this matrix multiplication, this special kind of multiplication, in order to project the population forward, an age-structured population forward in time, 1 year, 2 years, 3 years, or 100 years. And so that is the overview of matrix population models. What I'd like to do next is to transition into RStudio. And if you want to follow along in the lab webpage where it gets into matrix operations, you can load this R script right here. You could right-click on it or just click on it and save it into your course folder and load it up in RStudio, and we can just walk through it quickly together. Now this top line here just goes through the syntax for doing matrix projection modeling in R. This is the special character for matrix multiplication. If you just want to multiply something, like you want to multiply 2 times 3, you can just use the asterisk. But for matrix multiplication, you have to use this %* symbol, and that specifically represents matrix multiplication. Now this line won't run because we haven't defined projection matrix, or here, I'll just get rid of my workspace so that it's clear. So we don't have any object called projection matrix in our environment or abundance, the initial abundance vector. So we cannot do a projection yet. This is just going to error. This just gives the syntax for how we do matrix multiplication. But let's actually define this projection matrix. Let's build an actual projection matrix, and let's define the abundance vector. And if we can do that, then we can multiply the projection matrix times the abundance vector, just like we did here. The projection matrix times the abundance vector, and that'll give us the expected abundance in each of these age classes next year. All right. And it doesn't matter that this works with 3 age classes, 5 age classes, 50 age classes. It doesn't matter as long as the matrix is a square matrix that has the same number of rows and columns and the same number, and that number is equal to the number of stages. So it's very flexible approach. So let's build a projection matrix. We can define, using this assignment operator, we can define a matrix with these numbers in it, and we define that it has 3 rows and 3 columns, so it has 3 stages. This is a 3-stage projection matrix, all right? So that's step 1. Now we've specified this first element, but we haven't specified the initial abundances. So let's do that. Let's specify the initial abundances, and we will put all the individuals in the first class, the first stage of the life history. And so we'll put 1,000 individuals in the first stage, 0 in the second and third stages. So now we have an abundance vector, all right? So the abundance vector looks like that. The projection matrix looks like that. And let's project forward. So now we're going to do the matrix multiplication operation, multiply the matrix times this year's abundance or the previous year's abundance in order to get the year 1 abundance. And that's just like multiplying lambda times the previous abundance in order to get the current abundance, right? And so this now gives us the abundance next year. Those 1,000 hatchlings, some of them survived and became juveniles, and that's all that happened, because if you look at this matrix, juveniles have no ability to produce offspring next year, so that there's no offspring next year, and juveniles can't transition into adults, so this makes sense. There's only juveniles in the population right now, or there's only stage 2 individuals in the population right now. Now let's project another year. All right, so we're going to do the matrix multiplication again. Take the projection matrix, multiply it by the total vector of individuals in the population this year at year 1, and that gives us the year 2 abundance vector. And now we have new hatchlings in the population, or new stage 1 individuals in the population. Why? Because the stage 2 individuals do have a fecundity associated. So they're able to contribute offspring into the population next year, and that's how we got offspring in the population in year 2. And we can do that over and over again, but if you're going to do something over and over again, you should probably use a for loop. So here we set the number of years we want to run. Of course, now I'm just redefining this projection matrix as this easier to write out term TMAT for transition matrix, all right? And we specify the initial abundance is equal to the same initial abundances we had originally. And what I want to point out is that in Lab 4, you're asked to do some simulation using matrix multiplication in R, and you can, if you define the projection matrix and the initial abundance vector properly, then you can reuse the rest of the code as is. You don't need to write your code from scratch. If you want to reuse my code, you're welcome to. This code can be reused without modification. I'm not necessarily expecting you to be able to code for loops in R. It is a great skill to be able to do that, but what I want to do in this lab is focus on the concept of matrix multiplication and matrix population models, and less on making you struggle with code. So let's we can just go through this quickly. What we're going to first do is make a storage array that's going to store the abundance of each stage in every year. So we're going to have year 0, year 1, year 2, year 3, all the way to year 20. So we're running a 20-year simulation. We're going to fill in the first column with the initial abundance. So we know the initial abundance. We have 1,000 stage 1, 0 stage 2, 0 stage 3. And then we're going to project into year 2 and year 3 and year 4 all the way to year 21. We're going to use a for loop to do it. So we're going to loop through all the rest of the columns here and update the abundance using the matrix multiplication. We're going to take the transition matrix times the previous year abundance in order to get this year's abundance. It's the same as this. Take the transition matrix times the previous year abundance in order to get this year's abundance. All right. So let's go back there. Let's run the for loop. And we can even set up a plot that will plot out the abundance of each stage over time. And so what I'm first doing is setting up a blank plot. Then I'm going to set up a bunch of colors in order to represent each stage as a different color. And then I'm going to loop through all the different stages. That is the number of rows or columns in the transition matrix, the number of stages, it's just 3 here. And for each stage, I'm going to plot out the abundance over time. All right, and it's going to be each in a different color. So now we have the abundance of each class over time, and all we have to do here is maybe add an x-axis. That's just representing each year of the simulation, and maybe a legend as well, just in order to make it clear which color represents which stage. And if I make this a little bit bigger and rerun the plotting code, it will look a little nicer. There we go. And if you wanted to zoom in, you can do that. If you wanted to save the figure, you could save it as an image and maybe load it up into Top Hat if you want. You could save it as a PNG or a JPEG, and yeah, so maybe name it, question 2A. I can't remember which questions are asking you to load images, but if you wanted to do that, you can just save it into your folder, and there you go. You have it ready to go. So that is the basics of running a simulation model using a matrix approach. A couple other cool things you can do with transition matrices or projection matrices. You can use the PopBio library. Now, if you don't have PopBio, you just want to go into the Packages tab over here, and you want to install the PopBio package. Right? And so you can just hit install, and that loads up all this functionality for doing population modeling and matrix population modeling in particular. And if you load up that, then you can take your projection matrix, or we called it TMAT if you wanted to use it's the same thing here. We named them the exact same thing. You can get the, I never loaded, so you have to load up the PopBio package first, and then you can use this lambda function in order to get the lambda of the matrix. That is really convenient because every transition matrix, this one and any other transition matrix, is associated with a particular discrete rate of growth. That is the rate of growth that every stage in the population and the total population is going to achieve at stable age distribution, right? So if you look back at the plot, our population achieves something like stable age distribution, maybe after 10 years or so. You see that stage 1 is more abundant than stage 2, is more abundant than stage 3, and that the proportion of stage 3 individuals, stage 2, and stage 1 individuals are all the same after that point. And they're growing at exactly the same rate. And that rate of growth, that multiplicative rate of growth, is called lambda. All right, so that's the lambda that is associated with this set of vital rates, this matrix, right? These birth rates and these survivals all together make a growing population with a rate of growth of 1.3, or about 14% growth each year. All right, so that is how we can compute lambda. And if you want to compute the stable age distribution, you can also take your projection matrix and compute the stable age distribution using the stable stage function from the PopBio package. And it gives you the percent of the population that's expected to be in stage 1, stage 2, and stage 3 at stable age distribution. So 63% of the population is in stage 1, 22% of the population is in stage 2, and 14% of the population is in stage 3. All right. So a couple of questions in Lab 4 ask you to initialize the population at stable age distribution, or stable stage distribution, right? SAD, stable age distribution. All right, so how to do that? Well, let's say we wanted an initial population size of say 1,000. But we want it to start off at stable age distribution. Instead of putting all the individuals to start off the population in stage 1, let's start all the individuals off in stable age distribution. So what we do is multiply that number by the stable age distribution, right? So if we do that, we know we should have about 631 stage 1, 221 stage 2, and 146 stage 3. It's that simple. Just multiply the stable age distribution by the initial population size, and that gives you the n sub 0, or the initial population. And let's round that so we have whole numbers. All right. Now, if we want to go back to this code, let's initialize. We're going to use the same projection matrix, but instead of initializing the abundance using this, which is all initialized in the first age class, let's use this new n0 that we made. That's going to have, this is at stable age distribution, right? So the correct proportion of stage 1, stage 2, and stage 3. Make that the initial abundance, and then just plot this out. And look how smooth it looks all of a sudden. This is a population that's initialized at stable age distribution, so it grows at lambda per year all the way through, starting from the very first year, unlike our previous model, which looked all wonky because it didn't start off at stable age distribution, and it's only getting to stable age distribution later as the population grows and as the simulation matures. So that is all I wanted to show you for now. Please let me know if you have any questions. Good luck with the lab. Have fun, and I will see you in lab.